So this talk is called Sonic Pi meets Erlang. Yes, that's right. And it's the first time we've done this. We don't know. This morning, we connected our stuff to, we've been collaborating on and off over about a year since we agreed to do this. And about 2 weeks ago, there's been this flood of emails like, hey, we're doing this stuff in 2 weeks' time. Maybe we'd better get it working.
Yeah.
And we hadn't met physically until last night. And we went off to a tea place and had a cup of tea and sat there and tried to get our stuff together. But you didn't have your Moog synthesizer with you and your kit and stuff, so we were just kind of chatting what we're going to do. And then this morning we sat up there, and for the first time we connected all this stuff together, and it worked. So that was the first time it's ever worked. So this is really rather experimental. We don't know what's going to happen. The plan, which I wanted about a year ago, was you were all going to download the Sonic Pi on your laptops, because you'd be told to do this prior to that. And I would have a conductor's pin, and I'd start waving it, and they'd all start playing music. I think...
Next year, maybe.
Can we promise that for next year? No, probably we can't.
I think we could.
Because then there'll be like this gap of 52 weeks, 50 weeks, and then, oh my God, we've got to do this in 2 weeks' time, and we'll start writing the code. So Sam reminded me yesterday that we have to have a roadmap.
Oh, yes, it's very important to have a roadmap.
So it's very important we have to have a roadmap. And we didn't have a roadmap at all. So I just quickly made up a roadmap of some of the things I want to achieve and what we want to do. Oh, why am I doing? I mean, I'm retired now, you see. I stopped being a programmer, so I can just do my hobby projects now. And I've always been interested in music, so I thought, let's do some stuff. And I'm interested in computers. And I have a load of synthesizers at home. So I say to my wife, there's no such thing as too few synthesizers. You just want to buy
There's definitely enough, because this one synthesizer is one too many for my wife.
So what do we want to do? Well, on the roadmap, we want to play the Armageddon MIDIs. And I didn't know anything about the Armageddon MIDIs.
Dark MIDI.
So, yeah, but this is one of the dark MIDIs. Yeah. And I didn't know.
Have anyone heard of dark MIDI? One person, two people.
Oh,
you're in for a treat.
And I didn't know about this stuff until this morning.
You can imagine, right, a MIDI scroll coming down, playing a piano, playing honky-tonky piano, or playing something very, very simple.
Yeah, so I just...
Or you can imagine going nuts with it as well.
Wait a moment, let's go. So this is... Can you hear me as well? Wait a moment. Oh. Turn the volume down a bit. At the moment, it's not very exciting. This is the boring start.
It's a warm-up, isn't it?
Because the nice thing about computer-controlled musical instruments is you can compose stuff that no human being could play. Could a human play? No. So by now, it's getting difficult to play. I couldn't play that. I can play Chopin, but I can't play this stuff. Chopin could have... Well, I was going to say, he might have composed this stuff, but he may well not have done. So wait a minute, how do we turn this? So it's not only musically interesting, it's artistically nice, because you see these pretty patterns that are coming there. So that's on the roadmap, isn't it? We need to integrate stuff like that. Hang on, let's stop it. How do you stop it? Right, and then, because I'm classically trained in music, we need the presentation of scores. So we want to typeset the music of John Stump. Now, how many of you know John Stump's music? Oh, he was a... They don't know John Stump's music.
I didn't know either, so.
He was a music engraver who engraved music by hand, and he didn't use a computer, and he wrote some of the most amazing music you've ever seen. So I'd like to be able to typeset stuff like this. Right. This is typeset by hand. This is engraved by hand. Now, I wrote Earl Guten, which is a typesetting program for text, but it's not a typesetting program for music. Music's got about 400 glyphs in, and it's got all sorts of conventions. Normal English text has only got, 50 glyphs or something like that. So typesetting this is actually a bit of a challenge. So we need to do that as well, don't we?
Well, so for me, I think Western music's quite interesting. But I'm also particularly interested about how we could take notation like this and add things it can't do, like timbre, like how the sound sounds. And thinking about how we actually notate that as well. So I think that the code stuff we're going to show you later is part of the way there, but maybe there's some sort of visual notation as well.
So we want to play music that's generated by computer programs, not by people. We want to display that in different graphical forms. And we want to start here, which is something that's simple that you can teach children.
Has anyone here heard of Sonic Pi? A few of you, good. That's good.
Sonic Pi is great because you can just type, the simplest program in Sonic Pi is play 80, which just means play MIDI note 80, a middle C. No, 60. Play 60.
Ping.
C. Yeah. And I'd always wanted to do this. So my goal, when I met Sonic Pi, I'd seen you use it, I want to make it distributed, because I like distributed things. So the Sonic Pi, as it is today, is something that runs on one computer, and it doesn't interact with other computers. But music, orchestras and things are about communities of people coming together and interacting. So I wanted to see if we could make Sonic Pi...
Terrible idea.
...distributed,
yeah.
so we could... Oh dear. Oh. There's my project.
But if it was to be distributed, Joe, well, what would the starting position need to be?
Right? The starting thing is, to make it distributed, we would need two Sonic Pis to talk to each other.
Right, okay.
So I'd had this idea. I'd been playing with Sonic Pi, and I bumped into Sam at various talks, and I'm very impressed by what he was doing. He's doing some great stuff. And my goal was to make this distributed. So this is the foyer of the Station Hotel in St. Louis. Where both of us, I was giving a keynote at Strange Loop, and Sam was there. And I said, well, I'd really like to talk about how we can make this thing distributed. So we sat down here.
I think it was these seats, these ones here.
These seats? No, I think it was round there, wasn't it? Just round the back there.
Not sure. Yeah.
I can't remember.
I'm definitely sure it was these seats.
No, I think it was round there.
Well, that's our fight. Yeah.
We don't agree on everything. And so we had this conversation, and the conversation said, how can I control Sonic Pi from Erlang? And Sam said, well, all you have to do is open UDP port 4557 and send it an OSC message. I said, what message? Well, send it the message run code string. And I said, well, what's OSC? And he said, it's open sound control. And I said, what's open sound control? I don't have a clue what open sound control is. Everybody knows what open sound control is, said Sam.
Well, you all know what open sound control is, right?
Do you all know what open sound control is?
Some of them.
Yeah, well, that's all minus a few. So I thought, yeah, this is cool. So we sat there, and I thought, I don't know what this open sound control is, but we had the power of the internet, so I Googled Erlang, GitHub, open sound control, carriage return, and there was an implementation of the open sound control protocol. So I downloaded it and wrote that program. That's from my blog, actually, and where I describe what happened. And I literally typed in this program, and you see that run code Erlang in it, and the program says, play 50, use synth FM, play 60. And I ran it on my computer. It was separate to Sam was running it on his computer, so here's my computer, here's computer, and I ran that program, and it worked first time. Well, after we got all the errors out, but no. I mean, there's great possibility for spelling errors. No, and it worked beautifully. I mean, it just worked like that. And I thought, that's fantastic. So I had this, wow, here has somebody who's written a program that I can control from the outside. So how many of you have written programs that run on computers? Anybody here? So put your hands up if you've written a program that runs on a computer. Keep your hand up if that program can be remotely controlled through a communication interface. Really? Goodness. With a standard protocol?
Well, HTML, probably.
No. I'm not talking about... Put your hand down if the answer to that question is, yeah, it's running in the browser and it's HTML. Oh, that's better than I'd thought. And keep your hand up if you have specified the protocol in any kind of way, like with a session type or something, so that people can figure out how to use it. And written documentation. And got somebody else to use it. Oh, that's it. Come and see me afterwards. Tell me what your program does, and I will integrate it. Well, I don't know. That's amazing. You are. I think if I'd asked that in a big conference with thousands of JVM people, they would have all had their hands down. I mean, what is the point of writing a program if you can't remotely control it? What are we pissing around at? I mean, you shouldn't be doing this stuff. Okay, so at that stage, my understanding of Sonic Pi was that it was this thing that if you open port 4557 and send it a UDP message containing a program, it's a Ruby program, you send it, you could remotely control it. And I thought, this is the most interesting property of Sonic Pi.
Not the music.
So where's all the documentation? Well, there isn't any documentation. Why isn't it documented? Well, I don't want people to do that. Well, why? Well, because they might send the program RM-RF star, something in tiddly quotes, and we've got no security. So I don't really want anybody just to completely go in and kill everything.
So by default, it does listen on the loopback network, right? So you can't send it from another machine.
No, we can't. No. In case you're wondering. Because we're not publishing it. Right. And so what's this OSC stuff? It stands for Open Sound Control. And it's very inappropriately named. It should be called Open Anything Control, because you can use it to control anything. And it's very nice. Why are you laughing? I didn't say anything. Did I say something funny? Oh, never mind. It consists of a verb, which is like this. Where's the pointer thing?
Not really point.
No. Well, I've got a pointer thing, but I don't know what to press.
I can be the pointer.
Oh, bugger! I didn't press the pointer thing.
You pressed a...
No. Help! What happened? Oh, dear. It's a computer. That's what's gone wrong. No. Maybe just run up here. Why did that?
Is there a button you press that's...
Where do I get the light on?
There we are. It's good. It's good.
Well, but not press it again.
Just use me as the pointer, right?
Okay. Sam, could you kindly point it? Yes. Okay, so it consists of a verb. That has got back... That's actually a string. You shouldn't think backslashes don't mean anything. It's just a string. And an application can pattern match on that. And it's followed by a list of arguments. They can be integers or floats or strings. And it has a type descriptor. So, for example, the first one, where it says note on 123, 3.14159, and string, has got a type descriptor integer float string. And so by handing over this type descriptor to somebody, you can know what this is. So by documenting those, you have a strongly typed description of what those things are. Of course, you don't know what the semantics of note on are. So it's not self-describing in the sense that JSON or XML is self-describing. You don't tag up all the data items. You just name the message, and it's assumed you'll know what that means, and it assumes you know what the types mean. And that's a much better way of doing it, in my opinion, than JSON or something, because just the size of the encoder and the decoder is at least an order of magnitude smaller than a JSON parser. I wrote the parser and everything myself, and I've written a JSON parser, an XML parser, and a parser for this. And I tell you, you don't want to implement an XML parser yourself. The reason for that is XML suddenly says you've got to include XML path as well. And it's like when you start, and you've got to also do that, and you've got to do thing. And basically, if you want to implement XML, you've got to implement every RFC on the planet and the entire internet and something to implement it. And this is very simple. It's like 100 lines of code or 50 lines of code, and there you are. It's done. Right, so what happens next? Yeah, I said that.
And people do use Open Sound Control.
Yeah, they use it for all sorts of things.
There's robotics. People use it for robotics. You can pattern match things. You can say, actually, I want all the messages that relate to my arm, move them up and move them down. So there's lots of use cases of Open Sound Control.
So then I started digging into, a bit later, after we'd done this, we decided we would try and do something together. And I started digging inside Sonic Pi to see how it worked internally. And I found, to my great joy, it wasn't this one port. It wasn't like that thing on the top. If we expand that, it actually looked like this. It was built out of three components. A GUI, which you could command by sending messages to port 4557. A server, which was doing the logic of the GUI. The GUI had said, do this, play this, do this stuff. And a server. And the music, or the tones, were being generated by a program called the Supercollider. And the Supercollider is a thing I'd come across, and it's another amazing bit of software. And then, oh goodness, well, what about the Supercollider? It turns out the Supercollider itself recursively has this structure where it's built out of a programming language and a sound synthesis engine that actually has an extremely nice architecture. So I thought, yeah, this is really good stuff. And I looked up some documentation about the Supercollider, and it said, yes, the server is an independent program that will be communicated using open sound control. All you need to know is its IP address, such as, and its port. And the code that does that is 10 lines of code. If you can imagine the enormous difficulty of interfacing Erlang and C, or Erlang and Java, or Haskell and C, and Haskell and Java, and languages which have a different view of the world, languages which represent their internal data structures in a different way, are very difficult to interface. But interfacing through messaging is really simple. And Alan Kay will be here tomorrow, and he'll tell you how messages are wonderful, and this is the way we should interface.
And it wasn't always this way. So the early versions of Supercollider and the server were this one big binary blob, and there were some advantages of shared memory. But by separating them out to these two parts, James McCartney, who wrote Supercollider, he wanted to explore different languages to communicate with the synthesis engine. He wanted to try and see if Haskell would be an interesting language to write your end-user part in, or Ruby, or Smalltalk, or Erlang. And so by separating these things out, he basically opened up Supercollider for us to start playing with, and you as well, whatever language you want to work with.
So we started talking about this and what we should do, and Sam said, well, he wanted more or less a single abstraction. There's an additional thing in OSC which I haven't mentioned. That's timestamp bundles. So we've got commands. That's one set of things. Well, we can add a time in front of the command, and basically means do this stuff that's in the command at this time that's in the bundle head. And that should be done at a precise time. So, again, yes, that's a trivial program in Erlang. Getting it right is really easy, like 10 lines of code. And Sam's going, oh, I've wanted this for years, because it's really difficult to do in Ruby and schedule everything. So I thought, well, let's implement that, and Sam will be happy, and we'll see where we go. So I'm going to implement this as the first shot here. So the first thing I wanted to do was kind of figure out, when we're talking about time and the accuracy of time, I went into kind of geek mode and thought, has Erlang got sufficient timing accuracy to do music properly? Because prior to now, I've only done telecom systems, and the accuracy of the time is a few milliseconds, so that's pretty easy. So I'm thinking, is that okay, or do we have to go down to finer time scales?
It depends on whether the sound is actually independent sounds, in which sort of 10 milliseconds is probably enough. But if it's the same sound from the same source, then you'll get phasing issues if it's much less than that as well.
So I thought to myself, OK, let's do a few experiments. I've got a load of MIDI files. Now, MIDI files are just timed sequences of events. They are delta times and an event. And the event's a note on or note off, and you just wait for this. So the most simple-minded program you could possibly write, which plays a sequence of delta times, says, well, if the delta time is 0, you just send the MIDI event to the device, and if it's got a delta time that's not 0, you sleep for that amount of time, and then you send the message. That's really simple. You just iterate over that. And this sleep, that's just the sort of vanilla sleep in Erlang, the simplest sleep that you can possibly do. You just wait on a timer, and off you go. So that's a brain-dead program. That's a really simple program to write. It takes you 5 seconds to write it. And the question is it good enough? What happens when you write that? Oh, sorry.
Explain.
So it's distorting that.
It is distorted.
Why is it distorting? Sorry about that.
Just leave it, it's okay.
Oof, this is Chopin's Waltz in C-sharp minor, opus 64, number 2, if you didn't recognize it. I thought, yeah, that sort of sounds all right, although it sounded pretty lousily there because we had some crackle on the speakers. But is it actually okay? Well, so the next thing I did was, no, it's not very good. The reason it's not very good is the time is drifting slowly. And we're not aware of that fact, because every time we do a sleep, our brain is kind of relating it to the last time. So by the time we're at the end, we are literally maybe we're seconds out.
It depends, right? So you're using this on Erlang.
Yes.
What your design here is the first thing I did in Sonic Pi when I built it for the classroom in 2 weeks. And on a Raspberry Pi 1, Ruby running on that is much, much, much worse problem.
Okay, right.
You can really noticeably, audibly hear the difference. So it depends on how fast the architecture and how fast your language is as well.
So I thought, well, let's look at the timing to see what happens. And so I thought, well, OK, so instead of doing it that way, let's do it a different way. We'll measure the clock when we start. And then we'll measure the relative time in delta times. And then when we got to a particular point, I'll look at the clock and resynchronize using the time. And then and it turns out that Sam had invented exactly the same technique, this kind of musical clock that we resynchronize all the time. And I did it again. And let me see, I've got to change the slides here. Why doesn't this come up? There's a thing I have to press, but I can't see it now.
No.
Where's it gone?
It's probably just be pressed the right button.
Oh, I'll have to do it there, like this.
And then they can't see it, then it's fine.
Well, they can't. OK. You can't see the slides, but I can see the buttons I have to press in order to make it play things. Right. So
this is sloppy.
This is the bad one. Oh, why is it crackly? It's horrible. Oh, well, that's terrible. Sorry. And this is accurate timing. Well, it's not. Do you hear any difference? Oh, I can't know this.
I'm not sure what's going on. We'll just leave it.
Yeah, well, we can't fix that up. So that was better timing, although not perfect timing. And I wanted to understand why that was so. Oh! Oh, it does it when I press the button.
Yeah.
Oh, goodness gracious. Isn't that amazing? OK, right.
That's good.
Yeah, we can leave it there. So then I discovered that the Mac, if you say sleep for 50 milliseconds or something like that, 40 milliseconds, it actually is a bit late because it's trying to help you by conserving power. So it turns everything off and does things. And it takes it a little wee while to get started. And so it's always late. And there was a long discussion on the Erlang mailing list as why it is. So I evolved a new strategy to sleep to about 3 or 4 milliseconds until the time I really wanted, and then go into a busy wait loop, which is absolutely, I'm totally ashamed to say this. We couldn't find any other way of doing it. When you do that, you can get down to hundreds of nanoseconds in timing precision. But not always, because occasionally you're a whole hundreds of microseconds out. And this is not my fault. It's bloody Apple's fault, because they want to save power on the processor. And they do horrible things like balancing the temperature of the cores and swapping things out without telling you. So really, it's a horrible thing to program. But you can do it. And then I thought, wait a moment, because I'm programming in Erlang, and I like Erlang, so I thought, well, what's this representation of music? I've represented this the way you would normally do it. And how you would normally represent music is by a sequential program that basically sleeps for the next event and then does it. And I thought, well, hang on, why don't I create thousands and thousands of parallel processes where one parallel process represents a single note, okay? And what I'll do is, just to check the accuracy of the clock, I will create 19,000, well, I'll take a bit of music, which just happened to have 19,821 notes in it. And I would create 19,821 parallel processes, each with a little timer that plays one note. And I was kind of curious to see what would happen. Would the scheduling system manage to play this? Because now there is no synchronization at all. It's an orchestra. Imagine an orchestra with 19,821 musicians in it. No, this is a piano work, right? So imagine 19,821 pianists all sitting at a grand piano. The music they've been given is really easy to play because all they have to do is play one note at a particular time, and they're given a clock, and they say, you play this one note at this time, and they all sit there looking at their watch, they go, boom, at the right time. And I'm going to let a computer do that. So I was kind of, I didn't expect that to work because there's no synchronization at all. I didn't expect ordering to be preserved and all sorts of things. I thought it was going to sound horrible. So for the first time ever, you're going to hear a program with 19,821 independently scheduled events and just let the clock do the synchronization. And the first time, wait a minute, I need to make sure that it goes the right order when I press the button, so I'll do it this way. So this is the first one. because it's about 10 minutes long, this bit, it's... Oh. Did you start it?
Yeah, you didn't press it properly.
Oh, this is it. Can you hear it? That's what the orchestra's playing now. And then the soloist coming back.
It's like the dark MIDI stuff.
That's a coda.
Pause it.
No, just don't let it play. It's not that long. Yeah. And that's 19,821 parallel processes all doing their thing. So at this stage, I was going to, if you could kind of mentally slow that down in your heads, for those of you who are interested in piano music, who can identify that? Any guesses? Okay. So I thought, so what does it really sound like when we don't slow it down? Did it sound okay? So I've got the first bit just slowed down. This is, you're now hearing parallel processes triggering on a clock. They are not synchronized at all, and it sounds like this. Oh, shit. There.
No.
What?
Yeah, it's coming.
Sorry about the quality. And then the orchestra comes, da, da, da. Who knows what that is? Oh, dear. Oh, come on. No guesses. Oh, dear, I have to tell you. No, don't play that again.
Press it forward.
Yes, it's Rachmaninoff. It's the beginning of Rachmaninoff's first piano concerto. He did that when he was 18. Not bad, eh? Pretty good. So at this point, I'm thinking, yeah, we can do timing. We can do it down to hundreds of nanoseconds if we want to. We could represent music as sequences of parallel events and just sort of schedule them. And there aren't actually going to be any problems there. So I'm kind of happy with that. Let's see what we've got. So,
well, you haven't mentioned the most important thing, right?
So
you can totally imagine doing this in JVM, right? So I'm going to spawn a bunch of threads, sleep for whatever amount of time, hit the notes. Totally, I can do that in Java. Can you do that in Java? Right? It's not hard, or Ruby. The biggest problem, though, is that the garbage collector randomly decides to stop the world. And at that point, your music just pauses and then continues.
Oh, okay.
Right? And that's, and I think that the thing with Erlang, right, you don't have that problem. So you can play that program time and time and time again, and you'll never hear
garbage collect when it's doing it.
Yeah, or garbage collect per process rather than for the whole system.
Right. So back to remote control. Another way of looking at this is that there's a communication channel between the GUI and the server. And so a natural thought to me, at least, is, well, I'm kind of interested in what's going on there, so I'll put a little spying program in between that is purely a transparent spy. It's just watching everything. And I thought to myself, hey, that's rather cool, because I can now modify Sam's programs without him knowing. If he writes the word Sam in a comment in his code, I can insert a or whatever you feel like in the middle, and he won't know anything about it. And I thought that's a really nice way to do things. And this is a sort of Erlang-y way to do things. We observe the communication between processes. So I did that. And we got all that working. I asked Sam to modify Sonic Pi little place so we could allocate port numbers to it. And it worked, more or less. There was a little bug in the program. It worked pretty soon. And I got his trace like that. And I thought, that's cool. I'll send the trace to Sam. And I got this excited mail back that said, I completely understand what you're saying about the beauty of being able to see this interaction. I've already had a debug flag. It's been intensely useful. And he started saying, how long have you been able to do this? And then I mailed Mike Williams and said, how long have Ericsson been doing that? I think we first did it in 1974 or something. You know, we've always been able to do this tracing stuff. And one of the things people say about message-based systems, it would apply to any message-based systems, is it gives you a different level of abstraction. You've got black boxes that do things, and you've got the messages in between. And to me, it doesn't matter which programming language you use inside the black box, provided all the messages are the same. I don't care about programming languages. People are going on and on and on about programming language. Oh, we should program in Ruby, we should program in Python, we should program in Haskell, we should program in Erlang, we should program in C#, we should program in C++. There are thousands and thousands of programming languages. And I say it doesn't make a fig difference what you do. The most important principle in computer science is that of observational equivalence. If you've got two black boxes and you cannot distinguish them on the basis of the messages that are going in and out, they are the same. This is the most important principle there is. And Sam makes this wonderful system where I could just send a message in, it says, play some music, play a note, and it does it. And I don't need to care about how it works or how it's done inside. Because we are just looking at the messages, we can put other tools in place to monitor all this stuff. So the debugging you put in your programs is completely unnecessary. We can observe the behavior of your programs by observing the I/O that goes in and out of them. And that is the correct place to observe them. Because if we see that we send a message into a black box and we observe that the message that comes out from the black box is not as we expected, we can infer that there is something wrong inside the black box. And that's how to test things. We have raised the abstraction level to something that is reasonable. And we have done it, this behaves exactly as we behave. We send messages to each other. Other people can observe them. We can observe errant behavior by noticing faults in this communication. This is not the way we routinely build software, but it's the way we should routinely build software. Right, said that. So the architecture of this follows what I would call the Unix philosophy. The original Unix philosophy was we build systems out of small units, that each unit does something rather small and it does it reasonably well, and we glue these things together. The way that Unix glued things together was through the shell and through pipes. That, when you go into a distributed system, becomes sending messages through sockets or through UDP or TCP messages, and you have a standard way of encoding. The standard way of coding is very important because it's saying that all people should speak the same language. It's like, you know, I don't know how many human languages there are, but if we want to communicate, it's very convenient if everybody talks English, or if everybody talks French, or, I mean, when Britain's left the... oh, sorry. I mean, they'll hold the Brexit negotiations in French because everybody understands French. 28 countries understand French. Or what, I don't know.
Yeah, stitch the British up as well.
Yeah, right. So this OSC over UDP, it's actually the simplest way I can conceive of connecting things together. And so what we would like to do is just reinvent the digital audio workstation. These programs like Ableton and things, they are amazingly powerful, amazingly complex, and amazingly difficult to use. The problem with this approach is that programmers have made systems for non-programmers where they can manipulate every single musical event there is, not by writing text, not by writing a small program, because they've made this conclusion that people don't know how to program, and therefore they haven't given them the opportunity to write programs. What they have done is given them the opportunity to manipulate extremely complicated data structures by clicking on buttons and dragging dials and selecting things. And that is an appallingly bad way to do things. Now, Sam.
It's the alternative, right?
Completely the different thing. And said, let's do this in text, and let's start off with 10-year-olds to do this.
Well, the alternative, there is a protocol, right, which Ableton uses, which is MIDI, which is fabulous. But the resolution is 7 bits. You have 127 different values, which is totally useless.
Right. So to get a program to be remotely controlled, it has to respond to messages and do that. And we set this stuff up. The future. Sam wanted a bundle scheduler where we can send OSC messages. And we're testing it at the moment. We just tried it this morning. What we want to do there is, if you're playing one bit of music on one instrument, the time synchronization doesn't matter. But if we did an orchestra here, and we blast out, I want you to play the violins, and you to play that, and you to play this synth, and you to play that synth, they've all got a sound at the same time. If they're more than about, I don't really know, we reckon 10 milliseconds, something like that. If we're more than that, we're going to be screwed. So we don't want to do that. And now, I put this primitive in, and Sam's been using it, and he said he's written some stuff with it. I haven't actually heard this yet.
Me neither.
Sorry? You haven't heard it either?
No.
OK, so Sam hasn't heard it either. Now, Sam's basically a new type of musical instrument, where he's reinventing music using a computer. So he does this live coding thing. So in the future, a few hundred years' time, we're going to look back and say, well, Sam, he was like Mozart, or like...
There's lots of other live coders as well. I'm not the only one.
Oh, no, better. No, because when Sam can think something, he can think some music, and then he can write a quick algorithm that does it. So he can get... You know, do you realize how difficult it is to list? You know, he studied for years before he got good at it. You can play the fastest pianist in the world, Vladimir, what's his name, Horowitz, was reckoned to be the best pianist in the world. You can play scales faster than Vladimir Horowitz.
Which means you can too.
Yeah, well,
and everyone else.
Well, cheap, because we use a computer.
Exactly.
Now Sam's now going to show
a
you
10-year-old can
what we can do with timing and cheating.
Yeah, I mean, so...
Using programs.
Yeah, sure. So, are we running out of slides at this point?
Yeah, I think we have. I don't know. Well, it doesn't matter. That's enough slides.
Now, I've got no idea if the sound's going to actually sound good or not.
I hope it's not crackly like it was then.
If I take this away. So the goal with Sonic Pi has always been to try and teach computer science to kids, right? And there's a tough problem with that, which is kids really don't have much time to pay attention. They're not really focused on what's going on. And so you have to make things, look at the resolution of that, it's amazing. You have to make things really, 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 really simple. So we've seen this sort of play 70. Now, is this?
No sound.
I don't have it.
Oh, yeah, we've got locals.
Yeah. Right, so we've seen this, and Joe's talked about this and this, right? And if this is POSIX sleep, my desktop's nuts, then obviously you're going to get drift, right? Because you're not just talking about the time of... Because obviously sleep 1 says sleep for at least 1 second, not exactly 1 second, at least. You've got to wait for the scheduler to wake up. But also, line 1 play 70 takes some time to compute. Right. So you've got to count for all those
So good experiment. Take 2 distributed computers, play that program on both at the same start time, and just see if that works. Do they keep in sync, or do we need to do more than that?
Because in the early days, the reason why I really noticed it is that in the early days, this was no problem for kids, right? They were just happy doing this, play sleep, play sleep. But there was a point where the kids would say, right, this is my melody, love it, wicked, right melody, love it. Right, let's just make it a slightly bit more interesting. So sort of like that. Oh. Right. That was a melody, and then they also wanted, that's good stuff. I want to keep that, get rid of that. Right, and then we'd have like, I don't know, play 50. There's no bass, where's the bass? Oh, look at that. If you had a sub, that'd be like, right, synth, use. So you can change the synthesizer. I don't know, TB303. Right, and so let's do that, I don't know, 4 times. And see. Maybe this. Right, and so they'll have these 2 programs, and they would want to play them at the same time, right? And so, unfortunately, the computer science curriculum in the UK, which is fabulous, and we have one, doesn't allow you to do that because you need some sort of concurrency thing, right? That's typically taught at university. So I basically threw concurrency into Sonic Pi, and so you could do this, put these 2 things, and you could sort of say, in thread, do, like this. Oh, what's going on there? Now it's not working for some reason. Oh, yeah. That's because you can't hear it. Exactly. Right? And so they were writing programs like this, but they just sounded horribly out of time because of the same thing we were talking about before, the fact that this 0.5 is a different 0.5 than this because of the scheduler. This compute might take a bit longer, shorter than that. And then, of course, on the Raspberry Pi 1, all bets are off in terms of how fast the machine is. So it really was drifting quite badly. So that's when I invented the logical clock thing that Joe was talking about and made it all work in time. So now on this machine, it's totally fine. And so for a single machine, from talking to Ruby to Supercollider, it's all fixed. But everyone keeps saying to me, Sam, I like the Sonic Pi, but the synths are not that great. It's like, I'm sorry, I've invented them, I'm not very good at that. And I've got like loads of hardware. People say, got loads of hardware, how do I play Sonic Pi with my hardware, right? And the problem is that if I sent messages, MIDI messages from this program here at, say, this time here, it wouldn't actually, so the play 30, the way it works is it schedules the message ahead of time. So you've got to think of this as a program which is running concurrently, which is sending asynchronous messages to an external server, which is the music server. Each of these play commands is essentially a dispatch of a message. The message contains the timestamp of when you want things to happen in this open sound control thing that Joe was talking about. The server receives that message and then schedules it to happen, and everyone's grand. So we're not doing timing in Ruby, because that would be crazy. We're just doing management of logical clocks with Ruby, and that's actually fine. And the concurrency is fine, because A, we're working at human speed, not machine speed, so these are spinning 8 times a second. And B, the good thing about green threads is you can just randomly nuke them, and it's not a problem. You're not going to sort of wait for the machine to release its sort of handlers and things. But when we're talking to external machines, like this synthesizer here, we have a problem, because if I put a line of code in here which says, play my Moog synthesizer, it would dispatch that as soon as it ran the code. Right? And then the message would get to the synthesizer, it would play it before the Supercollider would play this, because this is scheduled ahead of time. And also, the delay of sending the message and receiving it is going to be subject to jitter. And so the timing is not going to be right at all. And then if Ruby decides to GC, again, you've got more jitter randomly all over the place. So although people kept saying, oh, there's loads of Ruby libraries for doing MIDI, you should just throw it in, it was never really a simple solution because of all these problems, the timing problems. And so what I really wanted in my head was, if I were to write something like this in, I don't know, Clojure or Ruby or something, the way I would write it would be to have a server which listens to messages. It would then spawn a thread, wait for a particular amount of time to make sure that it was the right time, and then forward the message on, right? That was like my head. But because of the GC problem, this is not really a viable solution on most languages. But the Erlang approach was exactly, idiomatically the same, right? And so Joe's like 30 or 40 lines of code just read exactly like that. And of course, spawning a thread in Erlang is insanely cheap, and there's no global GC, because each process is a completely isolated thing. And so it can really handle this timing in a rock-solid way, whilst a program isn't some hairy C nightmare where you have to write some horrible scheduler code, which I can imagine like the Linux kernel must be some nightmare for this. And so this works perfectly. So what we do now is I can now, instead of play 30 or this kind of thing, I can write Moog 70. And then we're getting the messages. No, we're not getting the messages. Oh, you've got something going there. Why is this not working? Am I getting any?
With multimedia, so I thought I'd make some lights flash.
Now it's done.
You can control all this stuff with these things. They're good fun. I wrote that yesterday.
No. Because this is obviously...
I mean, making lights flash, that's what computing's about, isn't it? It's not right in web servers and things. And making noises. Sorry.
What? Well, the message is going through, but they're not going through to the Moog thing, this C library. So this is Erlang here printing the messages, and then this is there's a little. So again, so that we're talking about the small processes. I'm not using Ruby's MIDI stuff at all. I'm sending open sound control from Ruby to Erlang. Erlang's scheduling it to be forwarded on to a little C library, which my friend Louis Lauret's written. And all that does is wrap around a MIDI library. So it just essentially receives open sound control and immediately dispatches it to MIDI. But we seem to be having some sort of problem with it. That's the Erlang bit, which works. That's good. And this... See, what is going on? It's found 0 MIDI inputs. It was doing this earlier, which is super annoying.
Well, it's the second time we've done it.
Yeah.
I mean, this morning was the first time.
So this little C library should actually recognize that, yeah, there we are. It's found it now.
Right.
So now, all right, we're good. So that's the Moog synthesizer coming out of these speakers, which is different from these speakers, right? And this is a piece of hardware which is entirely separate from the software inside of here. But if I play this louder and play them at the same time, you can hear them they're very, very closely aligned.
And we've got multimedia. Look, we've got flashing lights as well.
It's got flashing lights, right?
Yeah, I like flashing lights.
But
sorry.
This to me is like, just the fact that this works is a fabulous thing, because now I can control any MIDI synthesizer or any open sound control thing with the timing. Yeah. So what we can do? How long have we got left? Should we make some music?
Yeah.
5 minutes. Yeah. So see what we can do with this.
Make a noise.
Right. So let's just show you.
What was I going to twiddle?
Well, you can just twiddle all the knobs, Joe.
Just
go for it, right? So and also the cool thing about the thread thing is that you never really want to use you want to use this thing called Lively, which is much more fun. Oh, right. And then if I put the do there, and then I don't know.
Can I press these? Is that you or me?
That's this. Look. And so when you stop it all stops, and when you play it again. Probably hearing now acoustic properties, the fact that the sound is coming from different sources slightly differently. So, but generally it totally works, right? So what I've got here is 2 threads running. They're synchronized with each other, because you can totally do this. This one's playing the analog synthesizer, and this one's playing the internal Supercollider. But you can start to totally imagine, instead of saying my mode connected here, I want the mode connected on Joe's machine, and then start to figure out actually how to use Erlang to combine all these things. And the story for me was that, I didn't invent all these things. I invented nothing of this stuff. I just watched and saw other people's architectural decisions, right? So Supercollider separating out into these 2 things was a beautiful thing for me and made complete sense. And I had imagined, if I could have something that sat in between, like this Erlang thing, the benefits you could get were quite profound, right? So one would be, you could do this, right? That's the first thing. Scheduling these things, have them all in synchronization. But once you've got something sitting in the middle, as Joe was saying, then all you need to do is tap the messages and stream them to disk, and you have a recording, right? So all the events going out to both Supercollider and the Moog, I just put to disk, and then I can just play them back. Do some offsetting of the timing of the bundles, and I can replay all the things. But if I can store it to disk, I can also send it on the network, which then means then you could all be listening to the things I'm playing. So I now have screencasting for Sonic Pi, which doesn't require me to send video and audio and all that sort of nonsense. I'm just sending little simple messages, and you're able to essentially reproduce the sound on your machines. So then it allows me to do distributed streaming. But then, and this is where we're hoping to work for very soon, is that wouldn't it be really interesting if I could send messages to Joe, he could send messages to me, and we could jam together whilst you're in Sweden and I'm in Cambridge?
What would be really great from a discussion like this and a meeting like this and with people like you in the audience is if we could, I just call these endpoints. An endpoint to me is something that receives OSC messages. They're OSC over UDP. You can implement that in any language. You can do it in Haskell. You can do it in dependent type systems. You can do it in whatever, you know.
People say, Sam, you put it Erlang in. How many languages have you got in there?
You guys, you must have different expertise. I mean, I don't know how to do graphics. I don't know, you know, I'm crap at graphics and things like that. So somebody here and sitting in the audience who's really good at graphics, who knows C++ or knows, you know, Haskell or something, has got a really nice graphic, can just make a simple endpoint that's got a graphics canvas, so we can just send a few messages, start defining it. Somebody else knows how to play MP3 files, make a little player, a little MIDI player, a little WAV file player, a little thing. Somebody else knows how to trap keyboard events off MIDI devices. Just contribute these things, come together and build this and specify them so we can build an open architecture for this kind of application. And by doing so, we can show other people how to build applications. Because the way we build applications of including code and running them and all gluing them together is appallingly bad. We need to break out of this. We have these things called microservices which go on the net, but they are completely badly named. They're not microservices. They are macro, huge, big, ugly services. Microservices, tiny little things of less than a kilobyte or something, just running locally on your machine. They're not things that selling money in data centers for IBM. They're not microservices. They're ways for big corporations to make a boatload of money.
You ever thought you'd be giving a speech to some musical backgrounds, like Tron?
Are we done? Or are we gonna? I think we're done, aren't we? Kind of. Okay, we're done. Yeah.
What about our instruments, like guitars?
Sorry?
Our instruments, like guitars, like that's okay, that's obviously gonna work. But what about like more analog instruments, like guitars, bass, drums?
What about them?
Well, can you plug them into that?
Because they're fabulous. So we're not trying to replace guitars.
No, but you want to play guitar and put it through that, so you can do the collaborative jam thing that everybody wants.
I mean, Sonic Pi itself also supports the ability to get sound in from the sound card and treat it like a synthesizer, and you can apply effects to all these things. So yes, you can already do that. So it's basically an analog input. Yeah. So that could be anything you can record with a microphone. Yeah. So one of my duets, I jam with a guitarist, and we pipe that into Sonic Pi, and I'm able to add effects that are also synchronized with the music quite easily. So flanges and all that sort of stuff, slicers. Yeah.
Oh yeah, so I should say what we intend to do is strip down Erlang, because it's like hundreds of megabytes at the moment. Just make it into about 10 megabytes and just squirrel it away inside Sonic Pi so it all gets distributed. And then we can start teaching kids distributed programming as well, because as well as just having like 2 Sonic Pis.
Yeah, why stop at concurrency, right?
Yeah, we'll do concurrency. But I mean, once you've got 2 Sonic Pis, and they've discovered that we can send messages, we could introduce a new notation, like your sort of Sam bang message. And on the other side, you could like receive message, and it could print it out on their screen. So school kids could start writing distributed programs.
Certainly, yeah.
And we could sneak in some computer science into this.
I've already sneaked in the parentheses around things. Right? Yeah. I've had to modify the Ruby syntax for that.
But we'll keep the lambdas and things out for a while. They can do that when they're 11.
Yeah. Any more questions? So it's also, I was quite making a small announcement. So this is the latest version. Well, actually, we're showing you beta of 2.12, which I just made half an hour ago or an hour ago. 2.11 on the Mac is released now. So this is the official announcement that it's there available. So if you have a Mac, you're free to download it now. Windows will be around on Monday.
And if you've got kids, 10-year-olds, and you want to teach them programming, I think this is the best way I've ever seen of. Because the shortest program is like Play 10, and it's not one of these silly things with graphic user interfaces, which I hate. It's a textual interface. We actually we communicate by writing, and this is the major way we communicate throughout the generations. We can describe things in text. It's brilliant. And there's been this horrible thing to replace simple textual interfaces by horrible, gooey sort of thing. They click on nonsense to do stuff. We should abolish this stuff.
Sam and Joe, ladies and gentlemen.
Thank you.
Sam.
Can I say one more thing? So, obviously now is like social time. There's the lightning talks going on, all sorts of cool stuff, which I'm sure you're going to announce in a second. But also, I'll be making some music here a bit later as well. And so if you want to have a sensible conversation and talk about development, then you need to leave this room. Okay, right, Joe? Don't shout at me if I make too much noise, but if you want to see what you can do with the system, much more than what I've just showed you now, come and see a bit later and see what you can do. Thank you.
So we've got lightning talks, we've got drinks, and we'll soon have Sam in this room as well. Right. Enjoy your evening.